all brute force. Okay, and during the design strategy, for each design strategy, for example, brute force, I think a lot of algorithms introduced to you, and also based on the analysis, all the algorithm have already the big O, the analysis. So I do hope that when we discuss a bit on the analysis, you know already the foundation analysis, and you may, do the analysis in order to prove back the big O, for example, because every algorithm have already the big O given, published based on the algorithm. Let's say certain algorithm A, the analysis, the BO is n squared. Then you know how to get this n squared. So this is the thing. That's why analysis is important in the syllabus. We cover for the first part, the first 4 weeks, for example, so that after you understand the analysis, then we can move on to the design strategy. When we discuss on the design strategy and also plus the analysis, you know already how, what is the BO, what is the whether it is uh, efficient or not for the algorithm, and this is the benchmark for you. Okay. Okay, we continue this. What is design strategy or technique? Sometimes we call strategy, sometimes we call technique, sometimes we call paradigm. Basically, the same thing. Okay, describe the same thing. Maybe you can call design strategy, maybe you can call design technique, maybe you can call paradigm. Okay. So, an algorithm design technique or strategy or paradigm is a general approach to solving problem algorithmically, algorithmically that is applicable to a variety of problems from different areas of computing. These are based on Anani Levitin, 2007, the edition for the book. The main reference for this subject is Anani Levitin. So, he defined the design strategy is a general approach to solve or to solving problem algorithmically that is applicable to a variety of problem from different areas of computing. Mean the design technique or design strategy actually used for solving problem and also applicable for any problem, even though in different area of computing. Okay, this is the design strategy. Okay, next is a method of specifying an algorithm. How we can simplify or we can describe or we can express the algorithm based on the design. Okay, number one, based on pseudocode. What is a pseudocode? A mixture of natural language-like construct. So we may use this in order to express or to write the step by step, because algorithm is a sequence of instruction, unambiguous instruction as we defined earlier. So we can describe step by step by using pseudocode. Pseudocode is a mixture of natural language like construct. Let's say maybe your natural language is Java, then you can use Java language. It's up to you. Maybe natural language, your language is English, then we may use English, or maybe Japanese, Korean, whatever. So this is called the pseudocode. Okay. And the second thing is you may specify algorithm based on flowchart. What is a flowchart? A method of expression and algorithm by a collection of connected geometric shape containing description of algorithm step. So starting with where we have the start, the circle there, put the start, and finally end with the ends, with end the process. And we have the input, we have the process, we have the diamond that describe the condition. Then those are the geometric shape you may use in order to um, visualize the step by step with certain conditions so that we can understand that the process of the algorithm. Okay, in practical, basically, we start with the flowchart. We draw the flowchart. Finally, after we finish flowchart, we translate into pseudocode. From that pseudocode, we translate to source code, where we can write exactly what we similarly what we write into the pseudocode. The difference from the pseudocode and the source code is pseudocode is natural language like, where we can describe it based on our natural language. And the source code, we cannot use the natural language into the source code because our compiler cannot recognize it. Okay, we have to write in programming language so that compiler is C compiler can recognize that the instruction. From that it will translate into assembly, finally binary code, and it will execute according to the computer process where we have the input, process, and output. These are the things that you have to understand the design strategy. Okay, any questions so far? Ada soalan?
Not yet.
Tak ada. Okay, good. Okay, next is overview of design strategy technique. So after you understand what is a design strategy, what is design technique, what is a design paradigm. So these are the 4 design strategy that's important and also cover for our we cover for our syllabus. We have only 4 out of maybe 10 altogether. So we have brute force and plus exhaustive search. We have divide and conquer design strategy. We have a greedy design strategy. We have dynamic programming. Those are the design strategy that we're going to discuss in a bit detail based on this syllabus, so that after we finish this, at least you have these 4 main important or popular design strategy for every for algorithm basically. Okay, and before that, in order to understand, I'll give you the analogy taken from Jones and Pesner from their book 2004. They use this analogy for certain problems, so that from this problem you can understand the core design strategy, core design technique, as I gave you just now, which with brute force, divide and conquer, greedy, and dynamic programming. Okay, look at this analogy. Suppose your cordless phone rings, but you have misplaced the handset somewhere in your home. You don't know where is it. Okay, to complicate matters, you have just walked into your home with an armful of groceries and it is dark out, so you cannot rely solely on your eyesight. So this is the scenario, right? So that you can understand maybe from this scenario the um, the design technique represented for each scenario based on the same scenario, so that you can see the characteristic of the design technique. Okay. Okay, this is the first design technique. I mean, design technique 1, based on the analogy what we uh, what we uh, what I gave you just now. Okay, based on the analogy, to find the ringing phones, you would ignore the ringing of the phone or you couldn't hear it, and simply walk over every square inch. This is a keyword, every square inch of your home, checking it to see if the phone was present. Okay, you probably would be able to answer the phone before it stopped ringing, unless you were very very lucky, but you would be very guaranteed to eventually find the phone no matter where it was. Okay, based on the scenario, based on this scenario and the problem, we can describe the design technique 1. So the keyword here in the red color, so every square inch, meaning that you try to find the phone and there's no, I think, advanced strategy, or maybe there's no strategy at all. What you need to do, just you go for every square inch in order to find the phones. Okay, maybe you can get the phone um, um, maybe you can get the phone without before it stop ringing, or maybe you will be able to answer the phone. That is another issue. Okay, the issue is here whether you can find it or not with that strategy. This how we can describe the first design strategy. Okay, and forget about the ringing phone first. I'll give you this the algorithm, the real problem here. What we call the algorithm called sequential search, and finally we map back to the scenario or the analogy what we discussed just now. Okay, so based on this sequential search here, okay, sequences here, this algorithm basically we try to find the search key, right? We have these two parameter, the array a 0 to n, where we have the array here, right? Start with index 0 until n minus 1. So we have this all the element inside it or item. So we have the search key k. So the problem is we want to find whether the search key k exists or not in this particular list or array. So how to do this? So basically you need to go through for each of the element or the index here, start with 0, 1, 2, 3 until n minus 1 for every each of index to find the k. If we found it for any location here, then we stop. Then we achieve the goal. That is the goal of searching, right? So based on this, we can see that here there's no, I mean, advanced strategy could be just in order to find the k. Let's say the k here in that the last index here, the search key here. So we find here, try to look at here, 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 and here until you found here. So that is the step that you need to do, because we cannot skip for all this, except you have to go through for each of the location in that particular array, then until you repeat until you found it. Okay, so this is actually the process of sequential search. Okay, next is bubble sort. Just now was the searching algorithm, searching problem. Now is sorting. What is a sorting algorithm? A sorting algorithm is given a list unsorted element or orderable element, right? And finally, our goal is to get the element sorted, to get the list sorted. So the sorting is based on maybe ascending order or descending order, or maybe what we call in more precise is if ascending order is in non-decreasing order here. Non-decreasing order, the Q here, here, non-decreasing order. What is the difference between non-decreasing order and ascending order? Non-decreasing order is ascending order, but more precise, basically, we use a non-decreasing order. Let's say we have the list like this: 2, 8, 3, 4, 1. Where we put in the ascending order, it become 1, 2, 3, 4, 8. Okay. Let's say we have the list like this: 2, 8, 2, 3, 1. So when we try to do that, the ascending orders become 1, 1, 2, 3, 8, right? But for the compared to this, if non-decreasing order become 1, 2, 2, 3, 8. This is a non-decreasing. I hope by using this example, you can see the difference. What is the difference between ascending order and non-decreasing order, or descending order or decreasing order? Okay, because the accurate, precise term would be the non-decreasing order, where we can handle the problem with repetition. Let's say 2, 2 here. This we can reordering based on non-decreasing order. Okay, clear?
Yeah.
Okay. Okay, the bubble sort. What is a bubble sort? The first is you want to sort the list, the item or the element inside the list in non-decreasing order. So the problem here is from the solution, basically perspective of how to solve in order to find that, to achieve the goal, which is to sort that the list, is we need to compare. To compare what we call the two item pairwise comparison. So like this, let's say we've taken this, we have to compare this 2 and 8. This is the what we call that pairwise comparison, whether this 2 less than 8 is 2 than 8 is maintained, and next we go to 8, 3. Which one? 8 less than, is this false? Then we need to swap this 3 to this 8, like that, and so on, so forth. So become like this is called the bubble, right? Until the list later on will get sorted. Okay, this is the process of bubble sort. So from here, from the pseudocode here, where basically we have I equal to 0, means start with index 0 to n minus 2, which is n size minus 2. We have a j equal to 0, n minus 2 minus I. And if j plus 1 less than aj, and when this true, like what I mentioned just now, I wrote just now, swap aj plus. So if this, let's say, this 3 and this 2, we compare here, when this aj plus 1 here is less than here, less than aj here. When this true, you will swap here. Swap. So this become 2, this become 3. This is the rough idea of the bubble sort. And these are pairwise comparison. And finally, next here. This like bubbles. Water bubbles. Okay. This actually the idea of bubble sort, and the basic idea how to solve the problem for the sorting in order to get that the list sorted. Okay, clear?
Yes, sir.
Okay, next, selection sort. This is another solution or another algorithm for sorting. Just now was bubble sort. This is a selection sort, which is another solution called selection. So basically the same thing. We want to sort the list, the element inside the list. Look at this. The idea is actually the foundation idea basically the same, where we have to compare two items here, compared to this. This is a pairwise comparison. But here to compare, if we compare with the bubble sort compare for each pairwise, but here we compare what? So here we have the minimum I assigned to minimum, where I equal to 0. When j equal to I plus 1, mean the next here, this 0, this 1, right? To the array. So I equal to this, we set the mean for the index 0. And finally, we compare if aj is 1 here, whatever here, and compare with here, aj compare this. If less than the mean is actually at index 0 just now. If this true, we update the mean. J assigned to mean. Maybe if this true here, let's say here 2 and this 3, right? Okay, this true, then we update that the mean, the new mean here is here, the new one. Not the 3. Okay. And finally, we have to, because this actually the loop here, the scope loop until this. The swap is outside the loop here. So meaning that With this here, we compare here for each of the element until finish and -1 here, and we update the mean. After we get the final mean, then we swap here. Okay, swap AI to a mean so that we can get the minimum. So when we get the mean, put on the left. Start with 0, maybe after that we move to the index 1, find the mean, update index 1, and next index 2, find the minimum, the final, update. And this is how basically the selection sort works. Okay, how does it work? And this also the comparison. We compare two items to find that minimum, and after that we swap. This is actually the idea of selection sort. And the main idea is also based on the comparison, which is pairwise comparison. Pairwise comparison, 0, index 0, 1, 1, 2, 2, 3, and so on, find the minimum. And finally, when we got the minimum, when we finish that loop and swap, okay, that is the idea from selection sort. It is slightly different with the bubble sort, also the pairwise comparison in common, but if we compare, swap, compare swap means swap, automatically swap until finish, and maybe round second is compare again, swap until the list get sorted. Okay, clear the example, the analogy, and the real example based on searching and sorting? Clear? Now we're going to conclude. Okay, now we're going to conclude characteristic of this technique, what we call technique 1 just now. Okay, first is a straightforward approach. Is it correct? Straightforward approach. Like searching, you want to search the key. Of course, you need to go through for each. That is straightforward, right? There's no other way. Other technique. And for the sorting, we need to put all the minimum on the left, maximum on the right. So we have to compare pairwise. Compare, put on the left. Compare, put until finish. That is a straightforward approach. There's no advanced strategy. Okay. Usually based on directly on the problem statement and definition of the concept involved. Okay. The problem statement, for example, searching, we need to find the search key for each in the list. So that is actually the problem statement. And the concept is we need to find the search key inside the list, that we have to go for it. Okay. And the second is just do it. Of course, just do it. If you want to find the key, the search key K inside, you just go for it. Every location of the array. Okay, but impractical for bigger instance, but for small instance. What does it mean here? So basically, if we have, let's say, million, if we have only 10 n equal to 10 size of array, the element or the list maybe is okay, no big issue. But if we have million, trillion, maybe it may take some time to complete, especially for the searching. We try to find that search key, and the key is located at the last of the list. Then you have to go through all the element, then you found it. That become the impractical for bigger instance. Okay. Number 4 here, easy to understand design. Of course, I think it's straightforward. Just do it. Easy to understand, maybe easy to design, easy to implement. Okay, and all these characteristics tell us about brute force design strategy, also known as exhaustive. This is actually for the later on when we is subset of brute force, especially for the problem under expropriations problem. Then the technique actually called exhaustive search. Okay, clear for this characteristic of brute force? Based on the analogy is basically we have to go for every square inch of the room or the space to find that the point. When we have the algorithm, then the algorithm basically there's no advanced technique. We just do, the straightforward or just do it. Whatever we think that is practical to solve it, that's just solve it. Okay, clear? Any question? Okay. Next is design technique 2, still using the same analogy. To find the ringing phone, you would take care of the ringing of the phone and initially walk over for each section of your home based on the ringing to see if the phone was present in the section. You probably will be able to answer the phone before it stopped ringing. You would eventually find the phone where it was in the section targeted. Okay, design technique 2 here slightly different with the design technique 1, where basically if the design technique 1 basically just go for every square inch without any strategy, I would say. Okay, but here we have a certain strategy where we divide the rooms of the house into certain section. Okay, we divide section and we try to find based on section by section. We may guess that maybe the phone ringing would be in the sections 2, for example. Then we may use that section 2 to find it. Okay, this is the rough idea of design technique 1 based on this strategy where we have to divide it into certain section. Okay, and look at this. Basically, we have a problem of size n here, which is the bigger size, and finally we divide by 2 here, half of n, and this is the first what we call sub problem 1. This is the second sub problem. That's why if you still remember, you relate back to our recursive algorithm. When we do the analysis, we have n over 2, right? This is actually the thing, n over 2. During the analysis, you have this algorithm. Okay, we divide into 2 sub problem here, and we need to solve it based on the same solution for sub problem 1 and sub problem 2 before we combine back to solve the original problem. This is the idea of the design technique 2. Okay, and based on the example, I mean the real algorithm, we have the binary search to relate to this design strategy 2. Okay, for the binary search, this is under searching. For the second search, we have to go through like all the arrays here, the element in the 0 until m minus 1. This is how basically the technique. But for the binary search here, where we need to divide into 2 subarray. We have the first subarray and the second subarray, where we have m is actually the middle. M is actually the middle where we split into 2 here. Okay, like this. When L plus R divided by 2, where we got this as a floor values, and when K equal to M here, return M, meaning that the search key is actually whatever the value inside the M here. Then automatically we found it. Then we terminate because we found already. If we K not equal to M here, so if K less than M, we need to compare the search key. If the value actually less than M values, so we need to find the search key for the left subarray only, the first subarray, subprogram. Or if the K greater than the value of M, then we need to find for the second subarray, which is the right subarray. This is how actually the divisions can be done, or the process can be done in order to find the search key. Okay, and finally we do the process for each. Let's say for the value of search key is less than the M, we try to find in the first subarray, the left subarray, and after that we divide again until the 2 and find whether it's a, let's say the second round is the K is the value is greater than the M, we find again for the second subarray, which is the right, for the currents of the subarray, and process it until the stopping, which is we found that the search key. This is the technique for the binary search. Okay, and another algorithm, quicksort, using this design technique for the sorting. Just now for the brute force, we had a bubble sort and selection sort as example. But for this design technique too, we have quick sort under the sorting called quick sort. So quick sort basically we have what we call the pivot. Pivot is actually the initial partition here, where we have the partition here. For the bodices just now we have the M, the middle value, but here is pivot, and we have to find the pivot value, the final, and when we found it, then we split into these two. The first subarray and the second. Mean the first is called the left subarray, the second right subarray. And finally we divide, and net we conquer for both. If A are here less than equal to P, P is actually the pivot or partition value, and here is A are greater than equal to P, which is actually the another subarray for the right. Okay, finally we have to compare for both concurrently, become recursive, until we can combine back in order to get the list based on the quick sort sorted. Okay, and the third example, also the sorting, merge sort here, also using the same concept, division, divide into two. Let's say we have the array here, and divide into halfly, equally half here. You see, these are 4 elements, they also 4 elements. Divide into half, and divide again into this half. And finally, when we got this single value, single item here, and finally we need to merge here, so that merge and sort. 38 is actually already sorted, 29 sorted, and 17 sorted, 457 sorted, and we combine back to larger problem or larger instance. So here we basically become sorted 2, 3, 8, 9, and 1, 4 here, and finally we merge together here to solve the original problem here, and finally the list is already sorted. Okay, this is the idea of this design technique too. Now it comes to conclusion. Clear so far?
Yeah.
Good. Okay, what is a conclusion from the analogy as well as from the example algorithm? First is divide instance or problem into 2 or more smaller instance. Basically, in most of the algorithm, divide into 2, and maybe some others like 3, but I don't see more than 3. So basically, divide into 2 or 3. And for 5C, so far I don't see algorithm can be divided into more than 3. Okay, but normally in general it can be divided into more than 2. Okay, and secondly, solve smaller instant recursive. Mean when divide into sub problem number 1, sub problem number 2, then we need to solve it based on the smaller instance, which is the sub problem, before we merge together so that we can solve the original, which is the bigger problem. Okay, and next is obtain solution to original or larger instance by combining this solution. Mean concurrently we use the same solution for each sub problem, solve it until you stop and back to the reconcile to the original problem, and finally we can solve the bigger problem. Okay, the most well-known algorithm design technique because it's quite popular, and all these characteristics tell us about divide and conquer design technique. And basically we have other subset or variants of divide conquer. For example, decrease and conquer, transform and conquer, and we have others basically, but this actually we don't cover this for your syllabus, and for you only divide and conquer. So this is about divide and conquer design technique. Okay, clear?
Yeah.
Okay, can we move on to the next?
Sir, nak tengok merge sort tu sekejap.
Ya. Yeah.
Yang bawah tu macam mana dia tahu 1, 2, 3, 4, 5, 7, 8, 9 tu?
So, during to merge here, you need to compare here and here. So, the detail you have to look at the source code, the pseudocode later. Okay. So, when we reach to this merge sort under divide mode, I will explain again how it works, the details. Now you just get the concept.
Okay.
Okay. Boleh move on to the next?
Boleh.
Boleh?
Boleh sir.
Okay, design technique 3, based on the ringing phone or analogy, what we did for the two design technique previously, and these are design technique 3. To find the ringing phone, you would simply be to walk in the direction or the ringing of the phone until you found it. And the problem here is that there may be a wall or an expensive or fragile bus between you and the phone, preventing you from finding. What does it mean here? Okay, for this design technique, basically, our aim, our goal is to find the phone based on the ringing. The indicator is based on the ringing, right? Our goal is to find the phone. Okay, so when we need to observe that the ringing phone and try to focus the direction, which maybe for this direction. When we think that the direction is there, then we just go for it without thinking of any obstacle during the process of finding. Okay, that's why sometimes you have to face certain obstacle like wall, like bus, for example, to prevent you from finding. This is actually the limitation of this design technique. Even though you can, based on the goal, based on the ring input as indicator, then you guess, oh, that is the direction, you go for it. But along the way, maybe you had to face certain obstacle. This is the limitation of this design technique, okay? Okay, look at this coin chain. This is a problem of, actually a goods problem to describe or to understand the greedy, this design technique 3. Okay, before that, you have to understand what is the problem here. The problem here is here. How can a given amount of money be made with the least number of coins of given denomination? So denomination is coins here. Let's say 20 cent. We have the coin 20 cent. We have coin 10 cent. We have coin 5 cent. We have coin 1 cent. And we want to the goal here. So we need to set the goal. What is the goal here in order to solve the problem? Is we want to find the minimum number of coin, or called the least number of coin. So the least number of coin, that is the goal. So we set the goal. And in order to solve it, we go for it. It goes for it in order to get the least number. How to get, basically in simple logic, is how to get the least number. Of course, we need to take the highest value of coin, right? Highest value coin. Because when take the highest value of coin, the denom, then finally we can get the least number of coin. That is the idea of this design technique. Okay, for this, the highest coin value is 20. So from the 36 given here, n equal to 36, the amount is 36 cents here. So we start with the highest, 36 minus 20, here's remaining 60. Then we have only one coin 20 cent. And the remaining, so basically, maybe we may use a 10 here, the second highest. So we have one coin of 10 cent. And after that, remaining 6 minus 5, because this is the second highest. One time of 5 coins denom, and remaining one is 1 here. So altogether is 4 coins, the list. This is the list, right? If we take 10, maybe start with 10. 10, we have 30 minus 10, 10 is we have 3 coin of 10, right? 3 of coin 10, remaining 6 here. We have 1 coin of 5, and we have coin 1 of 6. So altogether become 5. Become 5 coin. This is not the list. If we take 5, of course, we have more coins. In 1, of course, 36, the maximum coin, 36 coin. This is the combination. So the goal is to find the least number of coin. That's why we need to choose the highest value of denom, or the coins, the value of coin. Okay, this is actually the coin chain. Clear, Hadid, for this? Understand? Hello, anyone?
Yes sir, clear.
Okay. Next is a Dijkstra algorithm. I think you know already what is a Dijkstra algorithm. It is a sorted path problem. Given a weighted connected graph G, find sorted path from source vertex S to each of the other vertices. So we have a term single source, single decision. Find a sorted path from a given source that S to each of the vertices. Mean we have a starting and end with A to whatever point. And single pair given two vertices, find a sorted path between them. So this is called the sorted path, but the algorithm is actually one of them called Dijkstra. What is the Dijkstra here? So let's say we have A, B, C, D, E. These are the vertices. Let's say we want to go from A to E. We need to find which one actually the shortest path, which is actually the minimum distance in total in order to go through, from A to the E. So how to do this based on the Dijkstra algorithm? Basically, we need to scan this A to B. What is the weight here, the distance, and the A to C. So because in order to go to E, we may go to A to B and B to D and D to E. This is one option. Maybe we can go to C, C to D, D to E, or maybe you can A to C, C to E. So the idea here in general, basically, so we're going to discuss later on in detail. This is get the concept and the idea for this right here. So we need to find the minimum distance. We have to go through to check the adjunctions, whether A to B or to C, which one the minimum. When we compare, of course, A to C. Then we got C. And finally, C to E, we may go through A to B, B to C to E, or C to D, and D to E. And finally, we found that C to E is actually the, and finally we can get the sum or total of the total distance. And finally is A to C, C to E is actually the minimum. This is the idea of this one. And this is similarly with the coin chain just now, but the difference is the coin chain, we need to choose that the highest value of coin. But here we need to choose that the minimum weight. It depends on the goal. So if the goal is actually to find that the least number, then of course, based on the coin, we need to find the highest minimum. Here also we need to find the shortest path, the minimum, but here we need to find the age with the weight with the minimum. This is the idea overall of Dijkstra. Okay, clear? Before we conclude, any question?
Not yet.
Okay. So conclusion can be made here from the analogy as well as the example algorithm or the problem from the coin chain from this Dijkstra is first construct a solution to an optimization problem piece by piece through a sequence of choice that are feasible, locally optimal, irrevocable, mean not able to be changed, reversed, and recovered. Okay, before that, I need to highlight this optimization problem. What is this? Because this problem basically fall under approximation problem. Approximation problem means that we cannot get the exact solution. We may get only the optimal solution, where based on the coin chain or based on the Dijkstra, which basically we have many options as a combination in order to solve it. And finally, we need to find out which one actually the optimum. That is the problem here is called the construct a solution to an optimization piece by piece. Piece by piece means step by step, because as we discussed based on the analogy just now, we set the goal. What is the goal? The goal here is to find the optimal, and we just go for it based on that the goal, based on certain here, piece by piece, and the step is feasible, and finally this actually we can solve by locally optimal, not globally optimal, and finally irrevocable, meaning that cannot be changed or cannot be reversed, and cannot be recovered. Once we choose that, there's no turning back. That is the limitation of this design technique. Okay, for some problem yield an optimal solution for every instance, but for most does not, but can be useful for fast approximation. What does it mean here? Meaning that when we involve certain problem, approximate problem, and also optimization problem, so some problem, when we use this design technique, we can obtain the optimal solution, but not for every case. So some cases we cannot get the optimal. This is the limitation or the drawback of this design technique. So all these characteristics tell us about greedy design technique. Okay, clear? Any question?
Far, no questions yet.
No question. Can we move on to the next?
Yes, sir.
Okay. Next, design technique 4. Okay, design technique 4, basically we cannot use the same analogy because this is totally different based on the other three what we did discuss just now. Design technique 4 basically is a very different design technique and very powerful based on the recurrent relation based on mathematical problem, especially when involves certain recursive recurrence step. Okay. But we can understand it through this Fibonacci. I hope that you still remember the Fibonacci. Still remember what is a Fibonacci sequence? Okay. Recall definition of Fibonacci here. This is when Fibonacci 0, written 0, right? 1, these are the base criteria. If Fibonacci more than 1, which is start 2, then we need to apply this formula n minus 1 and plus n minus 2, right? And finally, we can draw this, we can visualize this where n minus 1 plus n minus 2, n minus 2, n minus 3, n minus 2, and so on until stop at Fibonacci 0 or Fibonacci 0 1. If 1 return 1, if 0 return 0, and finally we can have 1 plus 2, 0.2, and finally it will solve the problem, the ordinal, which is n, whatever n. If n equal to 6, finally we will get the what is the Fibonacci n equal to 6. Okay, and you can see here this is actually the from the perspective of actually the brute force style here, where basically we just write like this: if n equal to 1, if n equal to 2, return 1, and if sorry, this is not 1, this is 0 and 1. This if Fibonacci 0 itu 0, 0.1 itu 1. Return macam n minus 1 and macam n minus 2. Okay, so when we apply that, let's say n equal to 5 here, so here 5, 4, this n minus 2, 3, right? This 4 minus 1, 3, 4 minus 2, 2, and 3 minus 1, 2, 3 minus 2, 1, and so on and so forth until we stop here. Stop, 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 and stop, stop here. But from here, you may observe some duplication or overlapping problem, where basically like this, Fibonacci 3 here, when basically after we pop this to get this for this sub problem, we have a solution here. Let's say the value here, the result here, and finally in this part we have also Fibonacci 3 and with the same. So basically this called the sum overlapping problem. So basically this problem is already solved, and finally we need to redo for this problem where basically this the same thing, which is 3. And similar with 1, 2 here, 2 here, and 2 here. We have 2, 2, 2. It's already solved. And 1, of course, it automatically will return 1, 0, return 0. Okay, it's already solved. Then we just get that the value. Okay, this is the problem of this problem. So from this design technique, basically we take care of this overlapping here by using this. Okay, where we have this array, and these are 0 and 1, and finally we check if Fibonacci not equal to 0, return already calculated. If n, then we use this. So meaning that if we have the solution for this, we store into certain, let's say for this array, keep it in table or record. And finally, when we solve it and we find that the same, then we just make use of the existing, the solution that already solved and make use of it without recalculating the same process. Okay, this is the design for. Okay, and okay, characteristics of this. The main idea, set up a recurrent relating of solution to a larger instance, to solution of some smaller instance, solve smaller instance once. This is a recursion as we did for the recursive algorithm. Record solution in table. This is actually the one of the main characteristics of the algorithm. So when we solve the problem, okay, once we keep it or record that solution in a table, whatever, in array, whatever, and extract the solution to the instance for the table, where we find that this is a similar problem that we have already solved. We already solved before. Then we just look up the table and you make use at the solution. So we can save that time. Instead of we for the sum overlapping problem, we recalculating the same process, so that it become actually is in term of computation become useless. Okay, become is inefficient. Okay, so it a design technique for solving problem defined by recurrences with overlapping subproblem, invented by American mathematician Richard Bellman in the 1950s to solve optimization problem. And all these characteristics or description tell us about dynamic programming. So programming here means planning. It's not programming as we think that as programming, computer science is a programming. It's a planning, how we plan. Basically, when we have a similar problem in the smaller instance, and finally the problem is already solved, we just take it, the solution, and make use of without recalculating the same process. This is actually the dynamic programming. Any question? Any question so far?
No, sir.
Okay. If no question, we move on to the first design technique called brute force. Okay. So from now onward, basically, we discuss on the design technique and plus all the example of the algorithm fall under the brute force in a bit details. And finally, when we discuss of the algorithm, the example, we try to look at from the design technique plus also the efficiency, efficiency, because we want to know whether the design technique is efficient or not. And maybe some of the problem can be, I mean, in terms of the design technique, can be done by certain design technique, for example, brute force, or maybe the other design technique. And finally, we can see the difference in terms of analysis or in terms of efficiency, time efficiency or complexity. Okay, brute force. What is brute force? As we discussed just now, a straightforward approach, usually based directly on the problem statement and definition of the concept involved. So some example, computing a to power n, where a greater than 0 and non-negative integers. For example, computing n factorial, where basically we can solve it directly, like the brute force, where let's say n equal to 5 times 4 times 3 times 2 times 1, something like that. Okay, and third is multiplying two matrices. We have a matrix A and B. We need to multiply A and B to become product of A and B. And 4 is searching for key of a given value in a list, like the sequential search, the searching technique. So these are some example in order to understand the brute force. Okay. Okay, brute force sorting. This is actually the same what we discussed just now, but these are a bit detailed. Selection sort. These are one of the algorithm introduced for, under the brute force. So selection sort, scan the array to find its smallest element and sort it with the first element. Then starting with the second element, scan the array to the right of it to find the smallest among them and sort it when the second element. Generally on pass I, where I greater than equal to 0 and I less than equal to n minus 2, find the smallest element in AI until n minus 1 and sort with AI. This is actually the what I explained, the same thing what I explained just now for the selection sort, where basically we need to find the minimum, start with minimum in that 0 and finally find which one the minimum and update the minimum. And when we update, the next is we need to swap. And again, we go to in that one, find the minimum and update until we swap. And finally, we can get, the final result, the list is sorted. Okay. So this is the algorithm. I think from here you can read that. This is a pseudocode, right? Pseudocode. So when we write the pseudocode, basically we have the name of the algorithm and plus the parameter here. These are the input. You still remember where we define the algorithm is the input must be valid or must be precise. So this we have to write the input is here is in array where we have input and array A 0 to n minus 1 of orderable element, meaning that we need to pass this the input for the algorithm is the algorithm that can be used to sort the element, orderable element. And the output also, of course, also in the array, sorted in ascending order. So we have this, I equal to 0 to n minus 2, and another loop is j equal to I plus 1 to n minus 2, do. So we compare this j and a min here and update j, and finally we swap. This actually the block here, right? This actually, and when this finish and finally swap here. So outside the loop for the second loop here. This how basically the selection sort. And time you see here, what is the big O here? Can you guess here? What is the big O? I think you can guess because based on the exercise given and also the example. So n squared, right? Because this until the n, even though n minus 2, and this until n minus 1. So n minus 1 and minus 2, basically n minus n is n squared. Then for the detailed analysis, basically, you may have this summation here, this n minus 2, this I equal to 0, increased by 1. This another summation is n minus 1, this I, j equal to I plus 1 minus 1. And then you can derive this, and finally, you get finally n squared. Okay. Okay, brute force string matching. This is another problem for the brute force. On top of searching, sorting, this is another aspect or another category of the problem called string matching. So string matching, where we have the brute force string matching. So what is a string matching? First, we have the pattern called pattern, a string of n characters to search for. The pattern is actually smaller than the tag. We have the longer, which is the tag, and we need to find certain pattern, which is the substring, and try to find that the pattern inside the tag, which is the longer string. So the tag is a longer string and of n characters to search in. The problem is find a substring in the tag that matches the pattern. So for the brute force algorithm like this, step 1, align pattern at beginning of tag. What is align? Meaning we need to go through for each character of the text. So that's align. First, move to a shift to the next until you find that the pattern. Step 2, moving from the left to right, compare each character or pattern to the corresponding characters in text until all characters are found to match. Subsequently search or a mismatch is detected, mean the pattern is not detected. And step 3, while pattern is not found and the tag is not yet exhausted, realign the pattern one position to the right and repeat the step. This is the repetition. So maybe from here, there's a pattern here. So we need to here compare here for each 0, 0, 1, 0, 1. So we need to align here. Align. So if we need to compare character by the character. And similarly with the pattern, let's say we have this pattern happy and this is a sentence we need to find here. Yeah. So we need to compare here. This happy here until we found here. This is how in general of this brute force. Okay. And this is the algorithm for the brute force. Here, let's say we have this input T actually for the text or string, P for the pattern, which is the smaller string, substring, and input is a T, is N character representing the text, P is character representing the pattern, output the index of the first character in the text that start a matching substring or -1 if the search is unsuccessful. So that's here we have to, this is actually the brute force. We have to compare for every character. There's no other ways, straightforward. Then finally until you find that the pattern. These are the for the brute force. Okay. So I equal to 0 to M to M. Why N to M? Because this M minus M is actually M is the pattern. So we need to start I 0 until the N minus M. N is the number of string. M is number of pattern. Okay, we deduct here. So J equal to 0 while J less than M. If J less than N, true, and P, J equal to I plus J do, and we need to compare align for each character. And finally, we increase J plus 1. If J equal to M, return I, and return M minus 1 if not found it. Okay, everything. What is the BO here? You can guess. What is the BO here? What is the BO? Can you guess what is the BO for this? Anyone? N squared. Why N squared? This anti M minus M, right? This anti M. There are two loops here. The inner loop, the outer loop, basically we can conclude as anti N. The inner loop anti what? Anti M, right? So this can be concluded as M. Not M, because the second loop is actually anti M, not N. Kalau M, then become N squared. This is less than N squared. This N M, so we can conclude that this Mn is element of still M. Correct? Is it correct? Because from here, generally, we can see that this I until the M minus M. If N, let's say 10, M2, M is 8, which is N. So we conclude this until N, right? And here is J less than M, which is not M. Mean if N2. So M times M. So we can do is O M N. O N times M. Because the second loop is not until the M, because this N with M. Not same with the N. Clear? Is it clear?
Yeah.
Okay. Okay, look at this. Let's say this is a process, the alignment just now. The step 1 here. With the step 1, align pattern at beginning of tag, moving from left to right. This is actually the alignment. So we need to align here. Okay, now, okay, move here. These are correct, these are not here. and move here, n to here, and finally here, here, and here, until we found here, which is actually the exact here, the pattern here. Okay, this how actually the what we based on the pseudocode just now, the same thing here, and we can visualize like this, the process here, the alignment, and also finally it will match the pattern, found the pattern. Okay, clear?
Clear.
Okay. Next is, this will be the last, closest pair problem. So what is a closest pair? Closest pair problem is a problem fall under geometric problem, dealing with points, polygons, space, and so on. Okay. So find the two closest point in a set of n point in the two-dimensional Cartesian plane, where we need to have the Cartesian x, y, where we draw actually for the 2D, that called the Cartesian plane. We need to find which one actually the closest, like this, like the pictures here. By eyesight here, maybe we can see this. Maybe this is the closest, right? This is not the closest here. But if we have this only, maybe we can plot the diagram here. We can see here, if we have millions, thousands, trillions of the pair like this, how can we to find that the closest? That's why we need algorithm. Okay. So based on the brute force, compute the distance between every pair of the distinct point, what we call the pairwise distance. Every distance we need to compare, and return the index of the points for which the distance is smallest here. This is how actually done. Okay, what is the application for the closest pair? Basically, the application. Let's say we have your item have now campuses, the your item campuses, the branch campuses, I think around 30 something or 40 something. So let's say top management need to decide to close down the certain campuses, which is actually the nearest. So we need to find that the closest of the branches, and when we find it, maybe you can close one of the branches. This is one of the application. And also maybe you can see that the plaques to becomes we have a lot of plaques. Then we need to avoid some collision of the plaque. So also this one of the application for the closest pair. Okay, and look at this algorithm here. So of course, if we want to measure the closeness of the pair, the points or the object, so we need to calculate the distance. The distance basically, in common we use the Euclidean distance, right? Euclidean distance. You know what is the Euclidean distance?
Yes.
So we have others distance method like Manhattan, city block. We have a lot, right? The Euclidean basically is a common distance. We try to calculate the distance. Okay, a list of P of n greater than equal to 2. So if we have only 2 points, then 1 point, then there's no pair. If we have 2, maybe you can directly get the point, the closest. More than 2, at least 3. And P1, xi, S1 and Y1 is with the coordinate here. This is X and Y, whereas the X, let's say 1, 1, the point here, the coordinate is object A. Okay, this is how actually we can imagine for this description. Output indices in that 1, in that 2 of the closest pair of points. So this is the output, actually we return the index, which index actually 2 indices, two indices that represent the closest of the point. Okay, we have the D means actually this minimum. We put the maximum, the infinity here. For I equal to 1 to n minus 1, for j equal to 1, j equal to I plus 1 to n, then we have to do this actually the Euclidean square root si minus xj squared plus y, this to this square root in the this actually the Euclidean distance, and get the distance based on the Euclidean distance. And finally, if the distance less than d mean, and after that we need to assign d to mean and return the I to index 1, J to index 2, and finally return index I index 1. So this is actually the process of to find the closest pair. So before we discuss on the detail of this again, what is the efficiency for this? The time O, BO what?
And
BO of and what? Hello?
where?
N1
Where?
and what? Again?
N kuasa 2.
Okay, n kuasa n squared, right? N squared, because this anti n, this anti n. Why this n squared? Like this. We draw like this because in order to calculate the distance, let's say we have x, this object I until 10. We have 10 object, right? So we need to calculate the pairwise distance like this. So this also xi until n here. So x1, s1 is 0, right? All this diagonal 0. And as how we x2, maybe these are the distance. Maybe this are distance. So finally, we got the symmetric here. And we need to find which one the distance minimum. Maybe here and this the minimum. Maybe x1 and x3 here. Based on the minimum distance for when we calculate all this. That's why this metric basically, n by n here, of course, this n anti n. So n times m, of course, m squared. Automatically, you can see that this will, in terms of tendency, become n squared. Okay? Clear?
Yeah.
Okay. Now, come to the conclusion. Brute force strength and weakness. What is the strength of the force? Of course, widely applicable. I mean, wide applicability. Because it is straightforward, just do it, then it's easy to understand and implement. That is the strength of the one of the strength of the brute force. Secondly is a simplicity, which is quite simple because the idea is quite straightforward. That's why it is simplicity. The third is strength, yield reasonable algorithm for some important problem. For example, metric multiplication, sorting, searching, string matching. When you use a brute force algorithm, become reasonable algorithm. We can get the solutions exactly without any further process, extra process or extra strategy. Okay, but however, the weakness of this brute force rarely yield efficient algorithms because most of the problem of brute force basically yield inefficient algorithm, n squared above. So because we need to, when we try to solve it straightforward, so we need to go through one by one the process. So that it's not inefficient in terms of complexity. Secondly is some brute force algorithm are unacceptably slow. Of course, when we try to execute bigger data, then of course become very, very slow. Okay, and not as constructive as some other design technique. These are the weakness or the drawback of this brute force algorithm. Okay, we finish until this. Overall, basically, what is the design strategy as overall, and also when we talk about the brute force, some algorithm belong to the brute force, and you know that the process very straightforward and simple and easy to understand, but in terms of time, you see it become a certain thing is not efficient and is not in terms of computational cost compared to others algorithm. And when we reach to others divide and conquer, let's say for the same problem later, we can see the difference based on the design strategy. Okay, any question so far? Ada soalan? Tak ada. So kalau tak ada, mungkin kita boleh stop di sini. see you tomorrow for the lab session for my group and also for the others group lab session with Cik Azizian. And maybe in the lab session, we may discuss on the solution for the exercise assignment 1, 2 for the analysis, and assignment 1 analysis for the recursive, non-recursive, and 2 for the analysis for the recursive, for example. Okay. And for this week, we are not giving you a new assignment or exercise. Okay. And because next week will be the semester break for the Hari Raya, and enjoy yourself for your Hari Raya. And when we come back, please focus back on our subject. Okay. So any question so far? Ada soalan? Ada?
Tak.
Kalau ada soalan boleh tanya, kalau tak ada saya rasa you boleh boleh keluar lah.